Hi everybody, welcome back. Well, I think it's time to get started on making some repairs on this thing. And this is probably going to be an interesting video because I'm going to start it out today. And over the next couple weeks, it's going to be a little bit crazy between, I have a lot of things scheduled at work, and then I have a week's vacation scheduled. So I'm going to be on and off the bench here, and there's probably going to be time gaps in between. So I'll probably forget where I left off. So if I repeat myself or any kind of thing like that, forgive me in advance because, well, I can't remember what I had for dinner yesterday, let alone what I did in an amplifier a week ago. So there you go. There's your disclaimer. So let's start out by removing this for now. I'm not going to be putting it back in. I get the concept, but I just don't understand. Well, it doesn't matter. So I got some solder here. This is good. Maybe we'll use this for part of the repair. How about that? Nice. All right, I'll save that over there. Let's see if this one gets warm enough or hot enough to undo this. Again, there's nothing twisted on here. They just kind of blobbed it on there. Like that. What are those? You're getting a solder in chat for this video, by the way, because a lot of you expressed interest in it. I'm just flattered that any of you want to hear my rhetoric. Oh boy. So these are made by ITT, but I don't see any part number. So I don't know. I'm assuming those are, well, let's see if they're Zener diodes. We're not going to be in any hurry in this video. We're just going to have fun and let things go. This will be a vacation video. What do you think? So I'll start with this middle one here. Oh, backwards. Go here. Looks like 15 volt Zeners. So if I go from here to here, I bet you it's going to be 30 volts. Yep, 28. You're not even seeing it. So yeah. So these are Zener diodes. So apparently they're just dropping some of the voltage here. And this is not a shunt regulator the way they're doing it. They're actually putting that as a voltage drop with these resistors. I mean, that works. I mean, you can do that. But you can see the kind of heat that made. I don't know. Well, creativity, I guess. All right, let's see if we can get this one off of there. This iron really isn't made to heat this big of an area, but it should work. Should get it enough. There, I just had that tacked on there as well. Get that out of the way. The nice thing about blob soldering things is that it's easy to take this stuff back off. So this I could probably just cut off. I don't even have to heat them up. This reminds me of those videos you see, you know, that don't have any words or anything. They just show you what they're doing. They play some goofy music in the background, and they just take components and just kind of like tack the leads all together and say, you know, billion watts amplifier, transistor, super, you know, both buzzword, you know, and then they do that and they hook a 9-volt battery to it and lay a speaker on its back and dump some nuts or bolts in the speaker to watch it bounce around. And yeah, and somehow those videos get, you know, 743,000 views. I don't know. You wonder how that works on YouTube, really. I don't understand all the algorithms and how they work, because I could probably try to do something like that and it wouldn't work for me. And the other thing I don't get is, well, I do get it. And I did this as an experiment on my video that I did a while back on the use of deoxit and, you know, how you shouldn't embalm your controls. And people got into this big argument over that I said that deoxit eats carbon tracks or something. But really what I was trying to say is don't overspray chemicals on a potentiometer because it will damage it. And yes, pots are made of carbon material, some of them, but it's not the carbon that's being damaged by the spray. It is the binding agent that they use to make the carbon, you know, form into that track. And by using all of those oily chemicals and things, it will break down those binding agents, and it will cause some of those potentiometers to be damaged, especially the ones that are attached to that what is it? It's not Bakelite, but that fiberboard backing that the carbon track is attached to. That adhesive will come off, and the actual carbon trace that's on there will just come loose. That's what I was trying to explain. I probably didn't do a good job because I am not a language major, as you all mostly know by now. But the bottom line is, hosing it down with more deoxit isn't going to fix a physical problem with something. It can remove dirt and crud and maybe add a little bit of a lubrication or a little coating to prevent future corrosion on metal surfaces. But that's really what it was meant to do. Nothing beats cleaning it the correct way. You know, everybody likes to have spray in a can that could bring us world peace and everything else, but the fact of the matter is, sometimes you just got to do the hard work, you know, and there's no easy way around it. All right, so let's take this apart. And then, by the way, when I am starting out with on the last video, if you recall, if you watched it, if not, go back and watch part 1. We determined that one of the channels must, in fact, have shorted transistors because you're getting the full DC rail voltage on the speaker terminals. And the only way that could happen is if you have a shorted transistor somewhere. It could be the outputs could all be good and one of the drivers could be shorted, and it's just turning the outputs on the whole way. If you notice, when I did the test, I had no load connected to the speaker terminals. That's really, really important. When you test these amps, especially ones that don't have a speaker protect circuit, you don't want to connect any load to the speaker terminals, not because you might damage the load, of course you might, but more importantly, you will then cause the output transistors to have to conduct very heavy current. And that very heavy current is what's going to cause heat in the transistor and is going to burn the transistor up and damage it. So if the transistors were still good, you just trashed them by connecting a load. So again, when you do an initial test on these amps, you want to do it open circuit. No load connected to the speaker terminals. And if you noticed, even though we were putting full voltage out to the speaker terminals, since it had nothing to dissipate into, there was no current being drawn, and therefore nothing was damaged. Okay, that's a little troubleshooting tip, a little troubleshooting trick you can do. So little things like that kind of go a long way to minimizing how many things you have to repair or replace when you're doing a service like this. And I don't even know how much of the camera I'm on here. Try to reposition this. I'm talking away. I'm not even talking or not even watching what you're seeing. Okay, we will be referring back to the schematic quite a bit. And what I did was, just like the phase linear 400, I did a similar thing with the 700 in that I reworked the schematic. I took if you look at the original phase linear service manual, they don't have one complete flowing schematic like this. They give you the driver board on one page, and they give you the output section in another page, and it's kind of hard to flip back and forth. So I just took them and stitched them together, using a video editing program, or photo editing, and then kind of added my notes and so forth, made any changes that I was going to make. And this should be, it may not be perfect. There may be some errors in it because I kind of did this quickly in the evening, but what I want to show you right now is the way this transformer works. I don't think all of them have this, but most of them have the dual wiring transformer in them. At least the two Series 2s that I have that. Maybe some of the Series 1s or so forth do not, but there's two primary windings on the big transformer. See them there? One here and one here. Yes, he's helping us. So for 120 volt operation, you just take the two windings and you put them in parallel. So you notice how this winding is tied to here and this side of this winding is tied to here. So they're just both in parallel. And the most important thing is you want to make sure that they're in phase with one another. If you were to reverse these two wires, how they're connected here, they would buck one another. So you just have to make sure you get, and the wires are color coded, so we can figure this out. If we were going to wire this for 240 volt operation, this wire that's coming up here would be connected to this one here. So it would come, the voltage would come in here, these two would be tied together, and then it would come out here like that. They would be in series. And again, the beginning winding and the ending winding have to, they have to be in line with one another. You can't reverse these wires with respect to this coil, or again, the transformer will buck. It will not. In other words, they will be out of phase. Those phases will cancel each other out, and this will look more like a short to your incoming mains than it will a reactive component. So all that being said, I'll show you how I knew that this was wired for 240. So right here is that terminal strip, and this is where, at least on this amp, where they have the ability to change the wiring for 240 or 120. And you can see I have two wires here, a blue one and a brown one. Remember, the blue wires are one of the windings, one of the primary windings. The brown is the other primary winding. And the stripe versus the plane tells you which one is the beginning of the winding and which is the end. And if you look right here, you have two wires, one of the start windings and one of the ending windings of the other tied together. See that there? So that represents the end of this coil. Where am I at? Here we go. Can't find myself in the camera. The ending of this coil and the beginning of this coil, that's the solid brown and the striped blue, they're tied together right here. Then the solid brown, and the striped blue are the two ends. So see how that is? So you have these tied together, and then these ones are the two ends, and you have your mains on there. And they're almost touching one another because they kind of soldered that on there a little crooked. But what we need to do to make this work is we make both of the striped wires, we're going to tie them together, both of the solid wires, tie them together, and then that's where your mains is going to tie into, just like the schematic is showing right now down here. So we're going to just have the 2 coils in parallel, and that'll be 120 volt operation. Now the reason that I'm doing this first before I do anything else is because I want to be able to, if I have to power this thing up to do any tests or anything like that, I don't want to have to deal with that transformer and all that mess. I want this to be wired properly, and then we'll move forward from there. And again, I cannot tell for sure whether this was factory like this. I'm guessing that it might have been, although this wiring on here, the way it was put on the terminals, well, yeah, I guess it could be factory. Could very well be. And you need a pretty hefty soldering iron for these, because these wires are very thick and they put a lot of solder on there. Just like so. And then we're just going to heat it up one more little time, and there it goes. And again, I don't know how much, each time I come down here on the bench, I don't know how much time I'm going to have to work. So if things get a little out of sorts, it's because I've been away for a while and I'm coming back to it and kind of figuring things out from where I left off. Now the next thing I want to do is just clean these terminals off. Get this solder. And yeah, you could use your desoldering pump, but to me that's not a very good, and this one here is stuck. So I have to, let me get another one. And you can use your fancy power desoldering station, but you'll clog it up pretty quickly with big blobs of solder like this. So if you have one of these pumps, they're a good investment. See how nice that cleans that off? There we go. Yins enjoying this yet? There we go. So we'll just clean those off. And then we have this orange and this yellow wire. And this is that other winding, and that's the low voltage winding that goes to the X and Y. Let me back this camera off here a little bit. So you can see these are the display boards, and you have X and Y, and there's a little power supply on these display boards, and it comes from this second winding down here. So you can see that goes here, and then you have these 2 little green wires. It's a low current circuit, and they go over and down into there, into the display board. And then you have one white wire here, one white wire here, and one black wire here. The white wires go to the power switch, I believe. Oh, one black wire goes to the power switch, the other white wire comes back from the power switch, and then this other one is your neutral from your incoming mains. So that's how that's wired up. So kind of interesting there. So we'll fix all that. But the first thing we need to do is figure out which one's which. The 2 center ones, strangely enough, they were down here. So we're going to kind of need to follow this, because I have a feeling somebody may have gone in and changed some things on here, but possibly not. And the other thing I noticed was, I'm going to undo this. All right. I'm just going to get this clamp out of the way for now. We'll put it back on, but I just want to get it out of the way for right now. And kind of slide these. Well, I'm not even going to mess with that. I just want to be able to get to things a little bit better. So Interesting. They have two of them. I see. So they have these two tied together. So those are the centers. And then they have these two. And they come out of two different ports on the bottom of the transformer. I want to make sure I get these correct, because if they're not, that's going to be really ugly when we first turn it on. The other thing is I have another bridge rectifier, a newer, better one that I'm going to replace this one with. It's a drop-in replacement, but it's just better quality. We're going to put some little bypass caps to reduce the switching noise. We'll talk about switching noise when we do that. So let's get these wires sorted out and figured out what they are. Okay, so I have the wires all separated from one another, and I did put little black marks on the ones that were originally tied together. And the blue wires should be one winding, and the brown ones should be another one, the other winding. So let's clip on. And you can see there's your low ohmage. And again, I'm not making good contact because of the crustiness on the wires, because I haven't cut them off yet. And then the brown wires here should be about the same. And you can see those are reading, that only reads a half of an ohm. We want to make sure they match, because they need to be exactly the same. So let's make sure we don't have a problem. It just might not have been making good contact. So let's, yep, points, there you go, same resistance. Okay, so the brown is one set of windings and the blue is another set. And I pretty much knew that, but I always check. You never know. Always check and make sure everything is as it appears. Now, I could probably clean these wires off, but what I'm going to do is instead I'm going to cut them. I have enough length, more than enough length, to cut these down and have fresh pieces of wire to put onto our terminal strips. So we're going to do that. Let's make it neat. Probably should use a little better pair of cutters than these little trimmers, but you know how it is. All right, and I'll strip these down a little bit. And I'm not a big fan of those, of the spring that makes these come back out, because it's awkward. And I'm not a big fan of those depth gauges on there. Some people hate that, but I rip all that stuff off of mine. And of course, me and the guys at work always get in debates over that, you know, whether to leave them on or, you know, you'll cut through the wires. Well, I can kind of feel when I hit the insulation on these, and it makes it a lot easier for me than having to try to read. And these things always come loose on me, and, you know, they're never the right, you never set them to the right depth. So I just do it this way. I guess after you do enough years of it, you get kind of used to it. I have some automatic strippers somewhere. I don't know where they are, but they're pretty cool. I didn't cut it off the end of this one, so it's like sticking. There. Okay, so now we have some fresh wire. So what we're going to do is the striped wires tie together and the solid wires tie together, and then your mains will go here and here, and that's going to be wired for 120 volt operation. So that's what we want. Okay, you should be able to see this. I'm not sure why they did this, but this is that other winding for the, you know, for the little small power supply for the display boards. And for some reason, this green wire here goes directly to this yellow terminal back here. But this green wire goes over to this terminal instead of right onto here, and then they have a very thin piece of wire just jumpering the two terminals together, which is a little bit crazy. So I'm going to move these over to here the way they should be, and that'll free up another terminal over here for what you're going to see here in a little bit. Okay, very interesting. Let's see if I can do this without having to refocus the camera. If you look right here, see that? That's a picture of a fuse, and it's rated by the schematic as a 2 amp fuse. That's what it said actually in the original schematic. And it's on that secondary, you know, that second winding there, that second secondary, yeah. Well, remember I told you there was a tiny little piece of hair in between those two? That was your fuse wire. That's called a fusible link. You don't see that very often, but that's what that was. So if there was an overload, that little wire there would break and open the circuit. Now, since we've removed that, what we're going to have to do is we're going to have to put a fuse in there of some sort to take the place of that, which I think is much better, because if that fails, I want to be able to repair it by replacing a simple fuse. So that's what we're going to do. Okay, so I have just a type GMA 2 amp fuse. It's going to be identical to what was in that fusible link. And then I just have a very simple little inline fuse holder. This thing's tiny. And we're going to put it right in line with this. So what I'm going to do is I'm going to connect to this in series with this, and then attach it into here, and then tuck it down out of the way. That other way. So probably should tin this a little bit to make it easier so it doesn't flare out when I'm... There we go. You guys having fun yet? All right. Nice. Okay. So I'm going to have to pull that down a little bit so it'll stick better. Okay. See, that insulation was pulling up and it got in the way and it kept the solder from flowing properly across the terminal. So we're going to heat that back up. There we go. Just let it cool and drop the pliers and we're good. Okay, so I took the wire that was under here and I moved it over to right here. So it's on this terminal now. And then I took the wire that was over here, and you can see I moved it over here. I haven't tacked it in yet. These two striped wires are going to go on this neutral terminal, which goes to that black wire, as we discussed earlier. So what's going to happen is this switched signal is going to come out. It's going to go into the soft start circuit. It's going to come out of the soft start circuit and then go into this terminal under here. So I have to put another wire under there yet, which I will do off camera here. And then we should have everything we need. Okay, so here is where we are so far. So I got this rewired properly, and I have the switched signal, and you can see where it kind of loops through from one side to the other, and that's going to go into this AC in and AC out. And this is our soft start board. You can see I made a little bracket for it, and it'll hold it. And I checked; it fits perfectly in here, even with the meters and every meter circuit in there. And I made this little aluminum backplate that's insulated. can take that off with this friction nut. And that's going to go in here like that. You can see how it's fabricated. It's just a piece of aluminum bar stock in there. And then underneath is the bridge rectifier, which I actually have another one of those that I am going to install. And I will show you what it is. It is one of these right here, and it's a 50 amp, 400 volt bridge rectifier. There it is. Here's the part number, if it'll focus. There you go. And this thing can take really high surge current. That is one of the good things. This one probably is not bad either, but it's old and I don't really know, what its ratings are. But I wanted to make sure whatever I have in here, it can handle what I'm doing. These capacitors are probably still pretty good, but we're going to go with a little bit heftier ones. Remember, these are like 5,000 microfarads. They're kind of low capacity for such a high current, high power amplifier. And really it's relying on the sheer size of the power transformer to keep the ripple current down to a minimum, which it does, obviously. We're going to get more into, I know we had some comments about, bypassing these with a smaller capacitor. And I'm going to tell you, I'm going to share my thoughts with you about that. I'm not speaking as an end-all authority, but I'll share my thoughts with you. And then you can go on the comments and kind of share your thoughts as well. But at least from my knowledge of it, where I am with this. So anyway, you can see, because I had to rewire all this, one thing leads to another. I'm going to rebuild the power supply before I even mess around with the amplifier section. I know when we get into the amp section, we're going to have at least one shorted transistor, if not more. We're going to have to deal with all that, but we're going to start off with a fully functioning, good power supply. I'm probably going to improve, some of the wiring on this. So let me get those slid in there and replace this little bridge with the new one. And we'll be right back. Okay, so I'm going to go through the process, and I know I've done this before in the past, but for those of you who have never seen this, it might be interesting to you. How to calculate the dropping resistor. Because remember, this relay that we're using is rated for 22 volts. See how it says DC 22? I don't know if that'll focus on it. There you go. So that means this coil of this relay needs 22 volts to operate properly. But we have a 95 volt power supply over here that we're going to feed it from. So you're going to need to have a dropping resistor, which is what this is for, to divide the voltage between this resistor and this coil. This coil is just going to act like another resistor. So you have two resistors, you have a voltage divider. So the first thing we have to determine is what kind of current is this coil going to draw with 22 volts across it. And then by using that, we can use Ohm's law to determine the voltage drop at that current that we're going to have with the resistor. So you'll see when I do this. So here's the coil of the resistor right here and here. Or, I'm sorry, the coil of the relay right here and here. And if I measure its DC resistance, that's what's important. The DC resistance is 2.46K. See that? So 2,462 ohms. That's the resistance of this coil of this relay. So 2462, right? And we know that we want 22 volts to be across it because it's rated at 22 volts. So if I take 22 volts divided by 2462, you can see I have about almost 9 milliamps. So let's call that 9 milliamps. 0.0089 amps, because volts divided by ohms is current. All right, so we know we need 9 milliamps. Let's keep that in mind. We have 95 volts coming out of the power supply here. This is going to use up 22 of those volts. So we go minus 22 volts. And the difference is going to be 73 volts. So I have to drop 73 volts across this resistor. And I know that I want to have 9 milliamps at 73 volts across that resistor. So if I divide that by 0.009, come up with about 8 kiloohms, or 8100 ohms. So a standard resistor value would be 8.2K. So something around an 8.2K resistor would be ideal for this to operate. Now, you got a pretty wide margin on that. It can be plus or minus, say, 500 ohms or so, and it'll still work. It's just, remember, if you exceed this 22 volts by too much, by more than a volt or so, this coil will get hot and it will reduce the life of the relay. If you go way too low, there won't be a strong enough pull to pull in the relay quickly. It might snap in, but not fast. It just kind of mushy will come in, and then its holding voltage is much lower. So the way a relay works is you have the operating voltage, but you also have a holding voltage for the coil. And that holding voltage is always going to be lower. So even though it's a 22 volt coil on the relay, you can have as low as maybe 10 or 15 volts, and it'll still hold the relay tight. As soon as you make that magnetic field and you connect that contact together, it doesn't need as much current to hold. So if we're a little bit lower than 22 volts during operation, it'll still work. So anywhere between 8.2 and 9K, let's say, will work. So let's find a resistor that will take care of that. The other thing is we need to know what kind of current, what kind of wattage it's going to have to dissipate. So if I take my 73 volts times the 9 milliamps, it's going to dissipate about a little over a half a watt. See, that's going to be 657 milliwatts. So if you put a 2 or 3 watt resistor in there, it'll run really warm, but it'll work. If you put a 5 watt resistor in there, it'll stay very cool, because you're exceeding it by a factor of almost, 8 or 10. So let's find an 8.2K 5 watt resistor, or the closest thing that I have in stock that'll work. All right, so the best match I could find were these two 18K resistors that I could put in parallel, which would give me 9K, which is more than the 8.1K, but it's going to be within, half a milliamp, plus or minus 1 milliamp. It'll be just fine. They're way overkill because these are two 7-watt resistors, but if you look on the board, they're going to fit pretty well on there. So I'm going to just go ahead and go with it. And that should take care of the dropping resistor. Okay, so it's been about 2 weeks since I worked on this thing, and I have gotten back to, I'm doing the power supply first, and this is kind of where I am. The new bridge rectifier is installed. I put some switching noise compression capacitors across each of the diodes in the bridge. The other thing was, the original amplifier, as the original design, had these 9800 microfarad capacitors, 100 volts DC at 125 volt surge. Surge voltage is only for milliseconds. It's not supposed to be there continuously. What I found is when this thing is connected up to 120 volts and wired properly, the B plus and B minus voltages exceed 100 volts. They go up to about 102 volts plus and minus. And this cap may have handled that, but a modern one will not. So I had to go to the next size up, and you're kind of limited with what you can order, and this is what I ended up having to order. And as you can see, I went with a Cornell Doublier, and Cornell Doublier, all right. And these are actually really good for this application. They are very low ESR. The ESR will even drop a little bit at kind of in the audio frequency range. If you look at the, I don't know if I printed that out or not. There was actually a ESR versus frequency chart, and it really favors this type of application. These are good for high ripple current, which is really what you're going to have when you're looking at an amplifier, because, you know, during peaks and huge bass passages and things, you're actually getting these big ripple currents, and they're coming and going as the music is changing. I was able to find this model right here. Let me see here if I can flip over to the correct page. So these are 150 volts with 180 volt surge. So they are well within, you know, I can go over that 100 volt range and I still have a way to go. And I found that this DCMX113U 150cc2B, that's a big mouthful, isn't it? But 11,000 microfarads, and the original one was 9,800. Very hard to find this size capacitor with much more capacitance than this in a known good manufacturer. There's ones on eBay and things that, you know, made in China. I don't know about those. I've never used them. Maybe they're really good, but I just don't want to try it out on this one. But if you look at the actual dimensions of the capacitor, this particular one, this 11,000 at 150, exactly the same size as this case. Same length, same diameter, and same lead spacing. So it'll be a drop-in replacement. And even though you really have to read the information on this, these DCMX capacitors, they're rated at 1,000 hours, which sounds like, you know, oh, well, there's 5,000 and 8,000 hour ones. But if you look at the way they're rated, and this is what we're using, the DCMX series. When you look at the way that they're rated, that 1,000 hours is using full load, which is maximum ripple current. I'm sorry, it's 2,000 hour life test. Ripple test is 1,000 hours. But 2,000 hours at its maximum temperature, 85 degrees Celsius. This is not going to go anywhere near that. As you drop temperature, operating temperature, a little bit, this increases by a whole lot. So these caps are going to last a very long time, believe it or not. Very good quality, and of course the name, you know, we've worked with those enough times that they're good. Now another thing I noticed was the original bridge rectifier, which was also pretty good too. This one has higher surge current and so forth. All they had were these little 18 gauge wires, one 18 gauge wire going to each capacitor. So this is a very short piece of wire. If I look up here, let's get some of this out of the way here so you can see. And I'm just going to clip onto this so that you can see what we're dealing with. So you're looking at about 4 milliohms. And when you're looking at something like that, 4 milliohms, you have to kind of take into consideration, I mean, that's just one little piece of wire. And if we go with our ESR meter, I'm just going to use this one because it's here. So if I connect this up, you can see even this old capacitor is 27 milliohms. So adding 3 milliohms to it, and I will tell you a brand new cap's going to be lower than that by a good bit. That makes a significant amount of ESR, believe it or not, that little piece of wire. So what I did was I went with these tinned copper wires, silicone, they're newer ones, and I did two 16 gauge wires in parallel. And when we look at that, let's hook it up and see if there's a difference. I'm not clipped on there super well, but I'm clipped on there, and you can see 1 milliohm. See how much, that little bit of difference, you might not think that makes a difference, but it does. And since I'm waiting for the cap in to come in, the capacitor to come in, let's talk a little bit about some of this. I get a lot of comments about bypassing capacitors. So you put your main filter in there, and then they want you to shunt like a little, 1 microfarad or 470 nanofarad film capacitor or something, like that's going to do something. Well, the whole purpose of that is at certain frequencies, especially very high frequencies, it's supposed to reduce the ESR. These caps, as you go up higher in frequency, the ESR will go up. All right, it's just a function of electrolytic capacitors. And the whole idea of your bypass cap is supposed to make it appear as lower ESR at higher frequencies. The problem is adding wires and things, as you can see, it actually makes a big difference in your ESR. Any gain that you would have by shunting a little cap across here, you're going to lose once it goes through the wire, all these wires, and wiggles its way out to the actual electronics. So really, if you're going to put a bypass cap in there, the right way to do it is to put the bypass cap right at the source, right at where you need it. So, for instance, in this case, right where these power rails come in, okay, which is, in this case, it would be the red over to this fuse here, the red and the black, and then those feed out of these bigger wires, and they go down into here. Down there is where you want to bypass it, after all of these silly wires. If you're putting it back here, you're defeating the purpose, because again, you're putting a resistor. These wires are actually a resistor, as we showed with the meter. You're putting a resistor between that bypass cap and your load, and it's going to defeat the purpose. So you want that little capacitor to be as close to the actual control element as possible. So it's funny, I see people, they'll go over here and they'll stack all these weird, they'll put a 1 microfarad, low ESR electrolytic, and then they'll bypass it with another, 0.1, 100 nanofarad film cap, and they'll buy these great big film caps that are, really expensive, audio grade, whatever you call it, and then they'll run a thin little wire over to the transistors, and they'll tell you how their soundstage sounds better. I don't buy it. You're going to have to prove that to me. The only way you will see a difference or hear a difference is if you bypass it at the control element, like I said. Does that make sense? Isn't it just plain logic? So that's what I'm going to do. I will bypass these, but not at this end. I will bypass it down here where it belongs. All right? Hope that makes sense. So anyway, the new cap should be in tomorrow sometime, so I'll come back. We'll get those fitted in. In the meantime, I also have the soft start board assembled, and you can see that right here, and I really shouldn't be touching that with them. Don't touch these with your fingers. That coating that they put on the outside of these ICLs, it actually will absorb the oil from your fingers, and it will ruin these. So if you touch them, if you brush against it, that's one thing, but don't be pinching them inside your fingers or anything, like to see if they're getting hot or something. Don't do that. That could significantly reduce the life of these. Just trying to give you a few tips. I ended up using a 9K resistor, which is these two 18s in parallel. That's what I had available. And I think I did a clip on how I calculated this. So that'll work just fine with this. So it's all wired up. These will go across the positive rail, your B+ rail. this is your AC in, okay, and there again this heavy wire, tinned wire, and this will actually basically the input loops through this ICL. Once the caps charge up to a certain point to where it'll activate this coil, it'll pull this relay in. The relay will then bypass this. The other nice thing is this starts out at a relatively low resistance. It's only a few ohms. So when this thing closes and opens, there's not going to be much of an arc across it because you're only going to have the small voltage drop across that couple of ohms of resistance here. So that's going to really save the contacts on this too. It's a simple design and it works. There's no use in doing these big fancy triacs and MOSFETs and all these things. You don't need it. This works perfectly and it'll last the life of the amplifier. Now another little comment I want to make is I just watched a video on the history. You know, I'm a history person. I like to read about things like this. But I don't know, a lot of you may know this, some of you may not, but the group Pink Floyd, who I'm a big Pink Floyd fan, I like their music and so forth. They used a whole bunch of these phase linear, the 700 and the 400s, on their early tours, especially the Dark Side of the Moon tour used them. And believe it or not, they experienced the flame linear effect, and after a while, they rebuilt a few of these things. They actually changed the faceplate on them. They gave a different name, but they would take these 700s and the 400s, and they would just add some of the things that you see me doing, like a speaker protect and some things like that, to make the amplifiers a little more reliable out in the field when they're using them. So, we're not doing something that other people haven't been doing for many, many years, I guess is what I'm saying. But if you get a chance to read up on it, how Pink Floyd used these phase linear amps, there was nothing like these amps at the time. So they're a piece of history. They really are. Now, I haven't really dug into anything on this, but I had to lift this board up to kind of get in here to do the power supply. I'm doing a power supply first, then we'll deal with the amp. But I can see we're going to have a few things here, because you can see this resistor here and this resistor here. You can see how they're cooked. And these have gotten warm right here and here. This, I don't know what this is all about. These are supposed to be 7.5K resistors. This one is a 7.5. This one, well, it is what it is. Let me back you out. You can kind of see here a little bit. This little resistor, green thing, and all that. So we're going to really have to do some work on this board to clean it up. But it does. The board, the traces don't look bad. They don't look like they've been soldered on or burned up or nothing like that. They look to be in good shape. There are definitely shorted output transistors in here somewhere. I'm going to have to find them and replace them. Probably going to end up having to replace the whole set. I'm not looking forward to that because, at between $7 and $8 a piece, and we have, what do we have? 1, 2, 3, 4, 5, 6, right? So I have times 4. I have 24 of these transistors at $8 a piece. You do the math. This is not going to be a cheap rebuild. But if I replace one, I'm going to replace the whole set. I'm not one to just replace one. If we're going to do it, we're going to do it right. Okay, it is the next day and my new capacitors came in. There they are for those of you who want to know what I ordered. And as you can see, they're an exact match. I mean, everything. So, drop-in replacement. These ones were 9800 at 100 volts, which these are kind of, I don't know. That was really pushing it. They were running this right up to its limit. And this one is 11,000 at 150. So I think these ones should last as long as this amp lasts. So let me get these installed and then we'll show you the finished product. Don't you just love these moments? So I have everything hooked up, but I do have the power wires here and here going out to the amplifier disconnected. So really we just have the bridge rectifier going into the capacitors. We are using the surge protector circuit, so that's all wired up. So everything should be here, and these caps should charge up. And as I said before, this thing puts out more than 100 volts. So that's why we went with the 150 volt caps. This is connected to the positive power supply. This meter is connected to the negative power supply that already has 2.5 volts in it, because these caps love to do that to self-charge. So let's turn it on, and I do have a 300 watt current limiting bulb in there in case something goes dramatically wrong, but hopefully it won't. Let's see what happens. And there you have it. Looks like we have plus and minus 101. Let's let it go and see how far it goes up. And again, this is unloaded power, but this transformer is so powerful that unless you really put a heavy load on it, it's not going to drop a whole lot. So we're up to 102 volts. Let's go direct. Hopefully it won't blow anything up. And it jumps up a little bit more, but not much. That 300 watt bulb is actually, there's no load. So we have about 103 volts. That is why I did not want to use a 100 volt capacitor in there. In the old days, these older capacitors were rated different. They would rate them at a voltage, but you had a margin of error built into the ratings. Today, you do not want to exceed any electrolytic capacitor, any modern one. I don't care how high quality it is rated at its maximum voltage, and the max voltage rating is truly the maximum voltage you should ever apply across that cap. So this one is well within its error. So now let's turn the power off, and you can see it's going to hold that charge there and bleed off very slowly. Now the positive supply has the relay on it. That relay is going to bleed down that capacitor, but it's not going to bleed this one down, as you can see. The other thing I want to check is the voltage drop across that, which I'm going to do that here next. But yeah, let me do that right now. I really don't want to disconnect my meter, but I guess I will. So let's disconnect this side. I'm going to put it here. I just don't want to short anything out. I'm going to connect this side right here, and we're going to look at the voltage drop across there. Right now it's about 54. So let's turn it on and see what it goes up to. So 79 volts. So if I have 79 volts across there at 18K, or 9K, I'm sorry, we're right on our 8.7 milliamps, which is right what we want going through that coil there. So that tells me that we chose the correct voltage. So that's good. Okay, so I'm going to take this back off right now. And you can see how long it takes to bleed them down. And I'm going to connect this meter back on here, hopefully without shorting anything. And let's just drain this cap down. I want to make sure we get that bled down. So let's do this one first. Okay, that's that one. Go over to this side. And I heard the relay drop out. And there we go. And I think we're pretty safe there. And you can see it'll pick back up a little bit. Kind of have to hold this on there a little bit. That last volt or so takes a little bit of time to bleed off. There we go. As soon as I let go, it'll try to come back up again. There we go. Okay. All right, we are at a safe voltage level. When you have big, high capacity capacitors like that, even if they have 4 or 5 volts on them, they will release an awful lot of current because of that capacity in there if you short them out. You know, that short-term surge current will be pretty intense. So you really want to bleed them down as far as possible. Okay, this is working. Power supply is done, and like I said, for the bypass thing, we'll do that after we complete all this. We'll place those bypass caps in the correct location on the amplifier. I think now we need to start digging into this section. So one last little note on this thing is my line voltage here is a little bit low. Right now our incoming line is 235 volts into my transformer, and remember it's a step down isolation transformer. So my mains voltage right here at the outlet is about 117 volts instead of 120 volts. So once again, if you have a really strong line that's between 120 and 125 volts, that 100 volts on this power supply is going to be even higher yet. It's 103 right now with 117 input. So you're going to be even further above that 100 volts. So again, I would recommend if you rebuild one of these amps, make sure you go to a higher voltage capacitor, which the next step up from a 100 volt cap at these great big ones, they don't have like, you know, 120 volt cap. Their 150 would be your next step up. So that's what this is. Just a little word of warning there on that. So that takes care of the power supply portion of this series. And when we come back the next part, I'm going to start working on this section over here. Now, I'm probably going to start out, and I may change my mind, but I'm going to clean up all of this over here, obviously, because of the mess that it is. And then I'm going to replace these transistors. Once I know that's all correct and neat and done correctly, then I'll focus on this board. And I'll probably I may even just undo this whole board from here, or let it hang by the wires, I'm not sure, like I did on the 400, and we'll go through and rebuild all of this, take care of everything on here. Once again, one of the channels is putting the full DC rail out to the speaker terminals, and so we'll have to rectify that problem, whatever it is. Obviously, you're either going to have a shorted transistor on here that's turning the transistors on the full amount, or you have physically a shorted driver or output back here on the heatsink. Regardless of what it is, you know, we'll need to find it and replace it. And you know me, I like to do things symmetrically. So if one side gets components replaced, even though the other side is still functional, I'll replace with the same components to make sure everything is always the same. So that's where we're at. And it looks like, for instance, some little things like this were replaced. Like this is a different cap than here. So obviously that may be factory, but it may have also been replaced at some time. Yeah, I can see this one was replaced over here. And kind of funny because the things that I did on the 400, like bypassing the capacitors directly on the back of the transistors instead of having a, you know, remote connecting them over here, notice what they did. So I think we were on the right track when we did the 400. So this is a little bit later model, I think, possibly, and some things were improved. And you can see this one has the upgrade. So that is the LF351 instead of the LF356. You just see a few things that they did differently on this one. And then, so I think this is going to turn out to be a really nice amp when done. I'm pretty excited. All right, so enough prattle here. As always, I wish you all peace, joy, happiness, and good health in your lives. And we'll be back real soon, and kind of in a hurry to get this done. I got 2 weeks here, and I'm going in for some minor surgery, and don't worry, it's nothing tragic. I'll be fine. But you know, whenever you have a procedure done, you're not allowed to lift big heavy items for a while. So I want to get this off the bench, and you'll see my next videos after this series will probably be smaller items. Maybe we'll do some theory or some kind of thing. If there's anything you would like me to do in that period of time, any kind of, I don't know, explaining things or something, or going over something, or test equipment video or something, let me know. I mean, I'm up for whatever. It's all fun for me when I'm on the bench here, because at least I'm not at work trying to figure out why some x-ray machine isn't working. So anyway, take care everybody, and we'll see you again real soon. Bye-bye.